So I'm going to go through some examples of stuff that you hopefully learned back in Physics 110. And these are things that I want you to be aware of because these are very common problems that you'll be doing in this class. You're learning a lot of techniques in Physics 110. That's kind of what's part of the beauty of Physics 110 is that while there are concepts involved, basics ideas of how motion occurs, more importantly, really, was learning techniques of how to solve problems. Kinematics, forces, momentum conservation, energy conservation, rotational aspects of things. So all these things are things that you learned. And so you're not really, in Physics 120, for the most part, you're not going to learn any new techniques. You're going to take all the techniques that you hopefully understood, and you're going to start to apply them to new phenomena, namely electricity and magnetism. So there isn't a lot of new basic physics that you learn. So anyway, in this example here, we have an electric field. Now, some of these problems are not going to be that familiar to you immediately because you don't know what an electric field is at the moment. But we have a charged particle here that is tethered to a wall, and there's gravity involved in this. So the charge that's here experiences a force due to the electric field, and positive charges experience forces that are along the electric field vectors. And so what's happening here is that charge that was tethered to the wall is now pulled out at an angle, because as the force is directed to the right, there's a tension that goes up and to the left, and the gravity vector obviously goes straight down. This is kind of similar to, actually it's not similar to that at all, never mind. All right, so when you want to solve, this is a force problem. You want to know what the angle measure is here. This is a classic force problem. So the way you start this off is you have a free body diagram. Now the only thing that you really don't know yet is what the form of the force is. The form of the force is down here, F sub E. It's the product of the magnitude of charge and the electric field strength. So you don't know that yet, but I'll just tell you that's what it is. There's no numbers in this problem. There's a number up here, but I'm not using it. Anyway, so let's draw a free body diagram, right? So got a coordinate system, label X and Y, indicating what the positive directions are. I got my F sub E, my electric force vector here. I got my tension up and to the left, and I got my gravity vector straight down. So the origin of the coordinate system represents the positive charge, right? And these are the directions of the forces that act on that positive charge there. The angle that is here is also the angle that is here. So if I were to draw a line, let me annotate things here. If I were to draw a line that goes straight up, okay, these angles are equal. The angle that's here and the angle that's here, they're equal. And so now also notice, and it's good to be mindful of this, your vector lengths. This should be, not only should you have the correct directions, but you want to be mindful of the lengths. This is a static equilibrium situation. This charge does not move. And so the x component of the tension vector, right, is matching the x component of the electric force vector. And the vertical component of tension, length, matches the gravitational vector. I mean, it's a small detail, but it's important. I think it's something to be mindful of. I mean, I'm not going to be crazy strict about that stuff unless you make your tension vector, look completely insane or something. If you say, oh, force is this way and tension's over here and gravity looks like that, I'm gonna come down a little bit there, I think. Anyway, so once you have that established, then we can write out Newton's second law. We sub our forces in the x direction. So we have our electric force vector that points to the right. So I have Fe here minus the x component of tension. So if I draw this, let me make a little thicker line here. So that's my force vector there, my tension vector. And of course, what we do is we do direct vector decomposition. So we break this up into its vertical and horizontal components. So you make a little triangle, right? And it's the components that we sum. And so we have to invoke our sine function for the side that is opposite, which represents the x component. So I have Fe minus tension sine theta equals 0. And then I go down to the y component, and going up is your tension cosine theta, because the adjacent side is along the y-axis, so I'm going to use my cosine there, minus Fg. Fg is just mg, right? So once you have your system here, well, the physics is done, right? That's what you had to do. In fact, really, the physics is this free body diagram. I mean, is this really physics here? I don't know. Probably, kind of. Not really. I mean, yeah, it is, actually. Well, you said equal to 0 because it's static equilibrium. But if it was a dynamic situation and this object was somehow accelerating, which is more common, actually, you'll be putting ma here, right? In the whatever direction accelerates it. So, but at this point, it's just math at this point, right? The physics is done. So we ultimately want, what do we want here? We want the angle. Okay, so we got to solve for the angle here. You got a system of equations. Well, that's fun, right? Well, I'm going to solve for tension here because I don't know tension, right? I mean, I don't have the numbers here. I can figure out the numbers, but I don't have tension. I got my mass. I got my electric field strength, right? I'll solve for tension, get rid of it. I don't want that there. So tension from the x equation is Fe over sine theta. I plug that into the y equation, which is what you see right. Oops, that's not an arrow. That's not an arrow. Son of a gun. There's the arrow. So I plug into the tension here, and then I can create this ratio, right? Cosine over sine. Cosine over sine's it's a cotangent, right? Flip things over though. Make it equal to a tangent. So tangent Fe over Fg. I put in what the form of these forces are. It's QE over mg, and I'll take the inverse tan, and then we got this beautiful expression for what the angle is. See, I love these problems. No numbers. You people like numbers. Why? If it was my choice, never numbers. Because this is beautiful. Look, the angle, it tells you exactly what determines the angle, right? If you're on a different planet, different angle, right? Got a different mass, different angle. And you can see exactly, inversely related here, the tangent function, it's increasing, right? So you bump up E real big, it's going to be a huge big angle. Okay, you bump up M really big, small angle, right? So anyway, that's cool. That's cool. Let's move on. Next problem is a kinematic problem. Uh-oh, what did I do? Uh-oh. Kinematic problem. Now this one looks crazy. I'm just going to walk it through here. Okay, this one looks crazy. This is a challenging problem, I'll be honest. We got a player plate capacitor here. We shoot an now again, you don't know the physics behind this at the moment. So, but the only thing you really got to know is how the electric field looks here. So if you have a parallel plate capacitor here, top is negatively charged, the bottom is positively charged. Then you have field lines that point up. This is an electron. That means the force is down, and therefore the acceleration is down. This mimics projectile motion under the influence of gravity. So what happens is this thing gets shot. Let me draw this. This thing gets shot, and it's going to head up, and it's going to have a parabolic path. And then, the force vector is down just like gravity, and then eventually it's going to hit here. And so we're trying to figure out, what the heck are we trying to figure out here? What is the maximum initial speed electric going to have by hitting the net? Oh, that's a good one. So yeah, here, if you shoot it too fast, it's going to hit the top. So we got to figure out what the minimum, so what that means, we're trying to look for like a minimum height, right? A minimum height, and the height is given here, 2 centimeters. So we got to work out the details. How fast can you shoot this thing so that it only goes up 2 centimeters and no more than that? That's the first kinematic thing we have. Then after that, we can figure out how far it travels the right, which is pretty much irrelevant. But let's go ahead and do it. So some information you need to know. You know what the magnitude of the electron's charge is, 1.6 times 10 to the minus 19 coulombs. And then I have the mass of the electron and the proton. I don't know why the proton's mass is here, but whatever. So we're not dealing with the proton right now. Do I do anything with that? No, I don't. It's weird. All right, anyway, and then down here are my kinematic equations. My kinematic equations. I like, this is how I like to do them. There's 3. Don't let anybody tell you there's more than 3. There's not more than 3. There's no 4th one. I mean, there's like some weird average thing. That's junk. Junk. Don't do that one. I mean, you can do that one, but I don't like it. And it's okay. You can do things I don't like. It's no big deal. As long as you get it right and you can explain yourself, I don't care how you do things. But if I can't understand it, it's not good. So anyway, those are my kinematic equations in there, and you know, I'm trying to figure out my height here. So based on what I'm given here, it sounds like the best thing to do would be equation number 3 here, because I know my initial speed is you know, it's that I'm looking for that, right? Final speed, well, the idea is that you're going to do things in the y direction, right? Because when you use these kinematic equations, right, there's x direction stuff and there's y direction stuff, and you never mix x and y direction stuff when you do your kinematic equations. So we're just focusing on y right now. So if I do that, my final velocity will be 0, because when you get up to that highest point, you temporarily, at least in y, your velocity is 0, and then you start to fall. So that means I have everything here. The acceleration is given by the electric force. You only have one force acted on this thing, and it's the we're not taking into account gravity here, by the way. That's not clear, but I'd make it more clear if we're doing this problem more seriously. But no gravity here to consider. I mean, like, the mass of the electron is kind of small, so you're not really going to have much going on there. So all right, ma equals QE. That's just the basic Newton's second law for this. So we have our value for A. It's E, capital E, over the mass of the electron. So I'm going to use equation 3, which is what you see right here. Final velocity is 0. The initial velocity is v sine 45, because this v is launch speed. So you want the vertical component of that speed, because you're doing everything in y, remember? Right? So minus, and I plugged in what A is right there. So I got this nice expression here, and I am going to put the numbers in here because it gets a little cluttered if you don't put the numbers in there, which is, clutter's okay, you know, but anyway, I threw all the numbers in here. All the numbers are given here, and I solved for V naught. So I kind of have I did a little of the algebra here. You don't see all that stuff, and by the way, get used to that. I'll show you the math when it matters, but I'm not going to sit there and do 10 minutes of algebra for you. All right, you all know algebra, and you should all know how to solve for V naught here, right? So I'm not going to go through all the algebraic steps. You do math, and you got a value for V naught. 1.2 times 10 to the 7. Fast, right? What is that? That's like, isn't that like 3% of the speed of light? That's crazy. Is that right? It's like 3% of the speed of light. Okay, anyway. Is this magnetic field? This is a pretty big electric field. Yeah, it is a big electric field. Another order of magnitude, you're going to have electrical breakdown of the air. Right? Yeah. Anyway, whatever. Yeah, it's good. Well, the reason I'm saying that is because, boy, electrons, 3% the speed of light sounds crazy, right? Well, it's good to question it. You go back and say, is it really that big? Well, you don't really know this yet, but the electric field this is a big electric field. This is real big. Anyway, all right. So once I got that number, I can now go into the other y equation. Okay. Oh, that's all I need there. But then to get how far does it travel to the right? Well, we have to figure out how far it travels to the right is going to be contingent on how far it travels, because the travel stops, right, when it goes up and then it hits back down on the positive plate. So what links us between the x and y is time. So we have to know exactly how much time is going to pass, okay, for it to travel across. So I'm using now the second equation here instead, and I put all my numbers that I have here, and I solve for time, and you'll get 2 times here. There's t equals 0, which is irrelevant, trivial, I should say, not irrelevant, trivial. And then we got this. Is that a 10 to the 9? That's wild. Well, it is going 3% speed of light, so that's a nanosecond, 10 nanoseconds or so is, I guess that's okay. And then we go to our x equation, and when you have the x equations for kinematics, this stuff all simplifies pretty simply, right? Because there's just one equation really, because you have no acceleration in the x direction. So you have your second equation, and you're just doing the stuff that's right here, and so we get 8 centimeters for that. No, that makes sense. That makes sense. I don't know. All right, example 3. This is an energy conservation example. Again, you're not familiar with all the physics here because you haven't had this yet, but we have a capacitor, parallel plate capacitor, charged to 500 volts. What that does is it produces an electric field that will point to the left like this. And so positive charges will experience a force that is to the left. The field's caused by the combination of the negative and the positive plates here, but ultimately we summarize a single field and a single force vector. So it's being pushed over to the left here. Now it's initially being shot at a pretty fast, no, not too fast actually for a proton. The idea here is that it's shot at the midpoint, and again, something that you don't know yet is that the potential decreases linearly through between the plates. So in the middle, it's at a potential of 250 volts. And so what we do is a potential difference of 250 volts is going to cause this thing to slow down. The question is, does it hit the plate or not? So the energy conservation here is kinetic plus potential equals 0. Okay. The energy transformation, I should say, is kinetic to potential. This is just like, you should imagine this is like you throw an object up into the air. Does it hit your ceiling or not? And then if it doesn't, you want to figure out how fast it's going to hit the ground. That's the idea, right? So that means energy conservation is conservative force here. We don't have friction or anything like that. So that means the change in the kinetic energy is going to be minus the change in the potential energy. And that's just simply saying that when one goes up, the other goes down, right? So what you don't know is that the potential energy difference is equal to the voltage, the difference in potential, times the electric charge. So that's the only thing you'll need to know for the math here, at least. And so we have a difference in the kinetic energy. We have an initial kinetic. And the way I'm going to approach this problem is this. I'm going to assume that it does not hit the positive plate. Now, there's a lot of ways you can approach this problem. You can assume it does. And that means your delta V is going to be 250. The other way you could approach the problem is to say, well, I think it won't hit the plate. And so if it doesn't hit the plate, what happens, it will slow to a halt before it turns around. So I'm going to set, then that's how I'm going to do this problem. I'm going to set my final kinetic energy to 0. And then I'm going to solve for delta V here. And I'm going to see, am I under 250 or am I over 250? If I'm under 250, I can't get all the way across. If I'm above 250, then I will hit the plate. So the idea is that is this thing thrown fast enough that it might slow down, but will it still hit? So I've solved for delta V here. So mass of the proton's a proton. And I had those numbers down here. Velocity, initial velocity squared. So I cleaned this up algebraically, and I got 209 volts. That's not 250. So we don't reach the positive plate. Okay. Now, if not, what will be the proton's fate? Well, it will turn around and start to accelerate towards the negative plate and hit it with a speed that would be a little faster than it would initially had, because it's going to go through an extra potential difference here. Now, what you hopefully might remember from kinematics, especially when it comes to throwing objects in the air, if you throw an object up into the air, assuming no air resistance, things like that. Say you throw it up with a speed of, I don't know, 15 meters per second. Okay, in the absence of air resistance, it's going to go up, reach a maximum height, and come back down. And when it comes back down, when it crosses the location of where you threw it, it will have the same speed, but in a different direction. So what I'm going to do is, in order to solve this problem, I already know, okay, that when it crosses the 250 mark here, it's going to be moving at 200,000 meters per second to the left here. So I'm going to simplify it in that manner here. So I'm going to do the same thing I did before, difference in kinetic energy. My delta V here will be 250, but it will be negative 250 because it's going to be a drop. I'm going to be going lower and lower. That will cancel with the negative that's here, thankfully. Because if you look at the way the equation's set up here, okay, you have your initial kinetic energy, and then the second term is positive, indicating that the kinetic energy will increase. And that makes sense. Like if you throw an object, again, up into the air, when it crosses your hand, it's going to have the same speed, and it will continue to speed up. So we'll hit the ground with a slightly higher speed. So then we just plug our numbers in here, and we get that it goes actually 50% faster, right? 3 times 10 to the 5th, which is only 0.1% the speed of light. Not too bad, right? Not too bad. So then we'll collide with the negative plate. Okie dokie. So that's how the energy is going to look there. And the last problem is a basic U substitution problem. Now, again, you don't know the physics of this yet, but we do a lot of integration at the start. We're going to have like maybe 2 or 3 lectures where you're going to be like, oh, this is not so bad. I like this. I can do this. And then like lecture 4 or 5, you're going to be like, what happened? You feel like you're going to get hit by a truck. All of a sudden, there's going to be integrals everywhere. Anyway, so don't worry about the setup here. Once we figure out how to break up this, because what we're doing here is we're trying to figure out what the electric field of a capacitor plate is. And the way you do that is you think about a ring of charge and how you would calculate its electric field. Then you expand that to a disk, and then you make the disk blow up to infinity, and then it becomes like a parallel plate. So anyway, so don't worry about the details there. When it's all analyzed and done properly, you end up with the integral that you see right here. In fact, if you're just like really eager, you're like, I want to know about this right now, then just go in the textbook. They derive this. Anyway, you end up with this integral here, and it's a simple U sub. It's r dr. And so r is our variable here. Z is a constant, but I can't take it out of the integral. All these stuff out here I was able to take out of the integral because these are constants. I'm integrating from 0 to r. So just in your mind now, all you're really thinking about is this. This is like x dx over x squared plus a constant, and all that's raised to the 3/4 power. That's just about the mathematics behind it, right? So now what's nice about this is a simple U sub. So we make U, I'm going to make U r squared plus z squared. Right? So we take the derivative of that, and we get du equals 2r dr. Well, look at that. We got r dr right there. That's nice, huh? So I will substitute that in. So now I'm going to have to divide this by 2, of course, right? So I get so this r dr is actually du over 2. That's why there's an extra 2 out front here. Now it's 4. And then in the denominator, it's u to the 3/2 power. And now it's just, so why is there a box down here? I don't know why there's a box. Oh, I never deleted this box probably. Okay. So that's just it's just polynomial. So we are going to, we add, so I imagine this is like a u to the negative 3/2, right? Don't ever use a quotient rule for anything, okay? I don't know what your math teachers tell you. No quotient rules. Bad stuff. Unnecessary. Make everything a negative exponent, and then use a product rule, right? Well, that's not even what's, we're not even doing, all right, whatever. That's not even happening here. This problem. Oh my goodness. Hopefully you can't hear that. It's like a lawnmower going on outside. I'll talk a little louder maybe. All right, so anyway, it's so you add 1, divide, and you get your negative 2 here. It's just a polynomial power rule, right? Power rule. Yeah. And so now, notice I did change the limits of integration. I like to do that. I mean, I know that instructors have different approaches here. Either they keep, what they do is either you make the U substitution, you do it, and then you put back in what the substitution was. And the easier thing really is just to put the limits 0 and r through the expression for U right here and create new limits of integration, right? So you don't have to do any new substitutions there. Okay, so you evaluate the limits here, clean this up a bit, and we get this nice expression right here. Oh, this is so good. I'd love to tell you all about it, but I'll wait till we get that, because it's, I love this last term here. Ooh, there's some special stuff going on right here, let me tell you that. All right, so anyway, that's all I got to say for this. The homework is basically, the 4 problems. Again, you're going to do the same thing. You're going to do a force problem, you're going to do a kinematic problem, an energy problem, but it's all physics 110 stuff, so it's not, you're not doing any electricity magnetism yet, but hopefully that will be it will go well because you remember everything. But if not, that's okay. If you don't remember everything, if you look at those problems and say, geez, I don't know what's going on here, well, that's fine. I'm here to help, right? Okay, that's it.